Welcome to this 22nd Hintze Lecture. It's absolutely wonderful to be back in person with real people in the lecture theatre, and this lecture is also being live streamed on the internet. So welcome to those people listening to us over the web. For those of you online, if you have questions during the talk, please put them in the Q&A part of the web browser, and the moderators, we have a couple of moderators down the front here, will collect your questions and ask them at the end of the lecture. So save your questions, type them in whenever you want, but they'll be saved up for the end. Okay, so I'm delighted to welcome, as the 22nd Hintze Lecturer, Professor George Efstathiou, Professor of Astrophysics at the Institute of Astronomy in Cambridge. Sir George has deep connections with Oxford. He was an undergraduate here at Keble College before he did his PhD in Durham. He was a postdoc at UC Berkeley before returning to Cambridge, where he joined the faculty in 1984. 4 years later, he was appointed as the civilian chair here in Oxford and the head of astrophysics, where he started building the department we have today. He returned to Cambridge in 1997 as the director of the Institute of Astronomy, and in 2008 he became the first director of the Kavli Institute in Cambridge. George's contributions to cosmology are widely recognized, and picking out a few highlights from a long list, he became an FRS in 1994. He was awarded the American Institute of Physics Danny Heinemann Prize in 2005 with his longtime collaborator Simon White, and in 2011 shared the Gruber Cosmology Prize with Mark Davis, Carlos Frenk, and Simon White. And in 2013, he was awarded the Nimitsas Prize in Physics. George's interests in theoretical and observational cosmology are extensive, and he's played a pivotal role in a number of key surveys, including the now ancient APM survey and the 2DF spectroscopic survey. He's played a huge part in recent studies of galaxy formation, specifically the development of the cold-dark matter paradigm, studies of dark energy, and most recently of the cosmic microwave background radiation. He was a member of the science team for the European Space Agency Planck satellite, launched in May 2009, which mapped the temperature and polarization and isotropies of the cosmic microwave background to unprecedented precision. It's my pleasure to invite Professor George Efstathiou to deliver the 22nd Hintze Lecture, The Legacy of Planck. Do we have a standard model of cosmology? George.
So thank you very much, Roger, for that kind introduction, and thanks for inviting me to give this lecture. It's been great to be back to Oxford and to see so many familiar faces and to see how the department has flourished. So I'm very grateful for this opportunity, and I'd also like to thank Michael and Dorothy for sponsoring these lectures. Okay, so now there's a perception in the academic community that for a beginning PhD student, the subject begins at the start of their PhD. Okay? So what happened before the start of their PhD is part of prehistory. And, you know, the papers are almost never referenced and, you know, and rarely read, okay? So I was thinking about this, you know, and how to present this this lecture, and I thought, well, I'll start at the beginning. Okay, what was cosmology like when I was little? And so here is me at age 3. So this is 1958, so a long, long time ago. What was cosmology like back in 1958? And the answer was that it really wasn't very scientific there was the big debate at the time was the debate between the steady state theory and the Big Bang theory. This is Fred Hoyle, proponent of the steady state theory, and this is George Lemaitre, who did pivotal work on the Big Bang theory. And very, very little data in which to test these theories. So, for me, if I go right back to the beginning, for me, all of cosmology, modern cosmology, is in the future. Okay, so that is what I decided to adopt as the theme for my talk. So do we have a standard model of cosmology? And, I could approach that question by showing you lots of plots of precision determinations of parameters from Planck and other data and show consistency and so on, and bore the pants off you, okay? So that's not what I wanted to do. What I wanted to do was to actually ask, what does it mean, to go a bit deeper, okay, into what does it mean to have, have we really established, what have we understood in establishing the CDM model, the lambda CDM model. So I hope that approach will mean that the talk will have some interest to people in other fields like exoplanets. So what were the key pivotal things that led us towards this cosmology? When I finished constructing the talk, I realized that there was a big downside to this approach because it looks as though I did everything in cosmology myself. Okay, so I wanted to be upfront about that, okay? This is my personal perspective, and those of you who know me know that I'm actually quite a modest individual, So Ofer Lahav is here, who's a very keen historian of the history of astronomy, and so he can put me right if he thinks I've over-egged any particular issue. So bear in mind there's that bias in this form of presentation, and please just indulge me, okay? All right, so Big Bang theory versus steady state theory in 1958. Really, cosmology at that time was almost a branch of philosophy, with people arguing about fundamental symmetries in the universe. The steady state theory is motivated by time translational symmetry as well as homogeneity and isotropy, but very little data to test the theory. So then the first major revolution after I was born was in 1965 with the discovery of the cosmic microwave background radiation from Penzias and Wilson. So they discovered an isotropic radiation component of microwave wavelengths that had a temperature of 2.7 Kelvin, around 3 degrees Kelvin, and as far as they could tell was isotropic over the sky, same temperature everywhere. But with the determination of the temperature, you could calculate the energy density in radiation and then extrapolate back in time, and the conclusion was absolutely incontrovertible that the universe began, at early times the universe was hot and dense. And there was further evidence that this was representing reality, because you could then calculate the abundance of light elements, the helium and deuterium, formed from nuclear reactions in this hot early phase of the universe, and that matched observations. So that really settled, the discovery of the cosmic microwave background settled the question, really, of the Big Bang versus the steady state theory. The universe began in a hot, dense state at early times. Now, immediately, the cosmic microwave background was discovered, theorists expected to see differences in temperature in different directions on the sky. They expected to see anisotropies in the cosmic microwave background. And so here is a space-time diagram, and we're in the middle, and this shows the paths of photons coming from two different directions of the sky. And the further things are away from us, We see them when the universe was at an earlier stage in the evolution because of the light travel time. So this shows the path of a photon. At a redshift of 1,000, the hydrogen is ionized. And so there's a very short mean-free path. Photons have a short mean-free path because of Thomson scattering with electrons. And then as the universe expands, it cools. The electrons and protons combine to make hydrogen, and then the universe becomes transparent. So photon is wiggling around when the universe is ionized, and then when the universe becomes neutral, the photons travel towards us in straight lines. So that's what's shown here. Now, if a photon comes to us from an overdense region, it's gravitationally redshifted. And if it's from an underdense region, it's blue shifted. So if we look in these two different directions, if there's a potential difference, the difference in the gravitational potential, these two regions, we'll see a change in the temperature. To order of magnitude, this is easy to work out. Okay, if the fluctuations are scale invariant, then the difference in the temperature is just the difference in the gravitational potential in these two directions divided by c squared. This is of order v squared over c squared, where v is the characteristic velocity of a nonlinear structure. So if we just stick some, just to get an idea of orders of magnitude here, for a cluster of galaxies, the velocity dispersion is 1,000 kilometers per second. So we would expect to see fluctuations of 1 part in 10 to the 5. So that's back of the envelope calculation. That's what we'd expect to see. We'd be very surprised if we didn't actually see that, okay? Or something like that. And so immediately there was a search for anisotropies in the temperature of the microwave background, which started in 1965. And we'll see how long it took before those temperature anisotropies were actually discovered. So then as Roger said, I went to Keble in Oxford as an undergraduate, at this time, so I went to Keble in 1973. The cosmic microwave background was still featureless. No anisotropies discovered in 1970, not even the dipole. Okay, and that was the state of cosmology. And so in my final year, I had to decide on what to do. And I was interested in particle physics, and I was interested in cosmology. So I went and had a chat with Dick Dalitz, who's professor of theoretical physics here, a famous particle physicist. And I explained the problem. I said, I'm interested in particle physics, I'm interested in cosmology, what should I do? And Dick said, there are lots of people doing particle physics, but cosmology is wide open. You should think about doing cosmology. It's just a wide open area. So either this was an incredibly diplomatic way of him saying, I don't think you're good enough to do particle physics, or it was very wise advice. Okay, so I'd like to think that it was the wise advice, but it certainly did pan out for me, because then I went to Durham. So here's Durham, 1976. At this stage, the cosmic microwave background is still featureless. Not even the dipole was discovered in 1976. So what problems do you work on? Okay, what sort of things can you do, on the theory side in cosmology? So I discovered, computers. So this is a picture of a computer of about that vintage, and very different from, the young people probably have no concept of what it was like using a computer back then, because you had to type out your program on punch cards. So you see here is a man in a badly fitting suit. You had to wear a suit to use a punch card machine, and you would write down your program and then you put it on punch cards, and then you weren't allowed to interact with the computer. You'd have to give your punch cards to somebody else, And you see how sexist this is. You know, it's the man operating the computer and the man writing the program, and the lady that feeds the cards into the machine. So that's what it was like. And what I decided to do was to write a computer program to look at the way that structure evolves and forms under gravity in an expanding universe. So I did the first large cosmological simulation. So here's an example of a simulation. This is exactly like the calculations in my thesis. And here's how it evolves. This number here is the expansion factor. So it tells you how much this box is expanded in physical coordinates, but it's all been scaled to what we call co-moving coordinates. But what initial conditions do you put in? What sort of, what is your starting point in a simulation like this? Well, we didn't have a clue. So the sort of problems that I was looking at were, idealized problems where you put in scale-free initial conditions and you evolve in an Einstein de Sitter universe, so there's no characteristic timescale in an Einstein de Sitter universe. And then what we expect is to see self-similar evolution because there are no scales in spatial direction or in the time variable. So we'd expect to see clustering settle down to self-similar solutions. So that was what I was doing in my thesis, looking at these idealized problems and finding self-similar solutions. So, and almost no data to compare any of this with. Then there was a revolution, and the revolution was the theory of inflation. So inflation was introduced in the early 1980s, and this solved a number of problems in cosmology by asserting that at some point in the very early universe, the equation of state, the dominant equation of state, becomes like that of a scalar field, so slowly evolving scalar field, so the pressure is minus the density. If you have an equation of state like this, then the universe expands exponentially fast, and so, basically faster than the speed of light. And causally connected regions can be expanded in scale by many orders of magnitude, and then at some point inflation ends. And this idea solved some fundamental problems in cosmology. So it solved the flatness problem and the horizon problem, principally. So that's the way that inflation is presented in a lot of elementary textbooks. But I can tell you that for us, working in the subject at the time, that was not the main selling point for inflation. The key thing was the growth of fluctuations, the generation of causally connected fluctuations from quantum fluctuations that get expanded in scale and become classical fluctuations. Now, there was a very influential workshop held in Cambridge, between the 21st of June and the 9th of July in 1982. And the participants arriving at that workshop, they were divided into two camps. So the idea that you could generate fluctuations, quantum mechanical fluctuations, and inflate them in scale, that had occurred to a number of people, and they tried to calculate this effect. And basically the calculations, there were two camps. On the one side, there was Guth and Pai and Andre Linde and Stephen Hawking. And they were saying the characteristic amplitude of the fluctuations is of order 50, is fatal to the theory. Okay? The other camp, that was Michael Turner and Paul Steinhardt, said, well, yes, you can generate these fluctuations, but the amplitude is tiny. So completely different results, one very high amplitude, one very low amplitude. And that was the state of play at the start of this meeting. By the end of this meeting, the whole problem had been solved. So it was a remarkable conference. And the key person who sort of solved the problem for them was Jim Bardeen, who is an expert in general relativity. And so some of the problems became were caused by the way that calculations had been set up that were dependent on the coordinate systems, which Jim Bardeen sorted out. And then the other key factor was people realizing that they didn't have to set parameters of the theory. They didn't have to set them at the Planck scale. They could choose the parameters, and that could they could basically fine-tune the parameters of a model to get the fluctuation amplitude that we expect today. So by the end of this meeting, the theory of the generation of fluctuations, from the quantum generation of fluctuations in the universe, the theory had been sorted out, and then the questions of the values of parameters became an observational question of what do we actually need, and then we can choose parameters to produce what we observe. So to us as a young generation working on cosmology, it was the generation of fluctuations that was the key thing that came out of inflation. Once we had that, we knew that the fluctuations were most likely to be adiabatic fluctuations with a nearly scale invariant spectrum. And then we could do detailed calculations. And so this is me and my colleague Dick Bond, and we started to calculate what we'd expect to see in the temperature. I mean, I gave you an order of magnitude Twiddles argument for the microwave background fluctuations. Now we could do proper calculations. And so this shows the power spectrum of the temperature fluctuations. So I'll show you what the results from Planck look like later on as a function of multipole. So this is basically the inverse of the angular scale of the fluctuations on the sky. This is about the angular scale of the moon. And this gives you the amplitude of the fluctuations in delta t over t squared that you'd expect to see on that particular scale. So what you see, so these were calculations that we did with funny parameters. These parameters look funny compared to the modern values, but nevertheless, the contribution from scalar fluctuations, producing a set of acoustic peaks, from gravitational waves generated during inflation, and from the sun. Once you've got a power spectrum, you can make maps of what you expect to see on the sky. And so this was a map that first map ever that we made of what we expect to see on the sky. And we could also calculate what the matter perturbations would look like. So this problem that I said, when I started my PhD, we didn't know how to start off numerical simulations of galaxy clustering because we didn't know what the initial conditions would like. Now we had models. So we could say, if the universe contains cold dark matter, say, we can calculate a transfer function, from initially nearly scale invariant fluctuations, and then run simulations and start to compare with the nascent redshift surveys that were being made at the time. So these are my collaborators. So you see, I was thin once, but I did take inflation rather seriously. So here's Mark Davis, Simon White, and Carlos. And now we were able to do simulations starting with realistic, inflationary motivated initial conditions. So these are some of the first simulations that we did of the cold dark matter model. So that's what things were like. And then I took on eventually a little group of students, to construct a big catalogue of galaxies. This was, Roger referred to this was the APM catalogue of galaxies. And so this was based on photographic plates, which we scanned with the machine in Cambridge and then stitched them together to make a big catalogue of galaxies. There are over 4 million galaxies in this catalogue with good photometric accuracy. And the motivation for doing this was we had predictions of what the large-scale structure would look like in the cold dark matter model with realistic transfer functions that, motivated by inflation. And so the idea was to get some observational data to test the theory. And as I said to my students, we will prove this theory. Okay, that's the aim. So we did it, and it didn't agree with the theory. Okay, so then the question was, why doesn't it agree with the theory? And so here was our proposal that actually the universe doesn't contain just dark matter, it contains a cosmological constant, large energy density contributed by a cosmological constant. And so this was the paper that we wrote. Now I'd moved to Oxford. So here is the conclusion, that if you have 80% of the energy density of the universe contributed by a cosmological constant, then you could explain the observations. And so here is what we found. This is the angular correlation function of galaxy clustering, and these dots are what we measured from that big galaxy survey, just in angular clustering statistic. And the linear theory expectation for a scale invariant spectrum is shown by these curves. So this parameter gamma is, so omega matter is the matter density in units of the critical density. H is the Hubble constant in units of 100 kilometers per second per megaparsec. The product of omega matter times H squared gives you the physical density in dark matter. Okay, so that's, you'll see that again later. But because we're measuring, we're extrapolating to, we're looking at galaxy clustering, which depends on the spatial coordinates, then we lose 1 power of h when we measure distances. So in the limit that the matter density in dark matter dominates over the baryonic content, the linear theory scales like the product of omega mh. So the physical density of the matter content divided by, and you lose 1 power of h from the distances. And, in great modesty, I named this parameter combination gamma, which is the first letter of George in Greek. Okay? And you can see for values of gamma of 0.5 to 0.1, you get these different curves. And the data is saying that gamma is about 0.2. And the value, the modern day value, is 0.21. And it was if you didn't have dark energy, you had to be close to 0.5, but that was clearly not compatible. There was more large-scale structure than you'd have expected unless the universe was dominated by a cosmological constant. Okay, so this picture of Margaret Thatcher, and you might say, well, what is Margaret Thatcher doing in this talk? So I was invited to Downing Street to give a science talk, amazingly. You couldn't imagine that with Boris Johnson, but anyway. So, and I went and I showed these, and I presented the evidence for dark energy. And Margaret Thatcher she found this so ugly that she resigned a few weeks later. So I gave the talk in September. By October, she was gone. if that is the way the universe is, it's not worth being prime minister. I mean, honestly. So, but the reception to the idea that the universe was dominated by a cosmological constant was uniformly badly received. Okay, and the reason that it was badly received was because, it's shown in this cartoon here. This is from a talk that I did at the time. So, with inflation, if you get a massive expansion in scales by many orders of magnitude, so our observable universe is just a tiny patch of the net volume that's been inflated, then the spatial curvature is just diluted away. And so you expect the density you expect for spatially flat geometry, the density parameter will be 1. And if it's 1, it's always 1, okay? But if you have a degree of spatial curvature, then there's in Friedman, Robertson, Walker cosmology, there's a late time attractor towards omega equals 0. In other words, you have to explain why is curvature becoming dynamically important now, at the Hubble time now. And that requires incredible fine-tuning. So inflation was a mechanism that solved this fine-tuning problem by giving us an attractor for a solution for omega equals 1 at early times. That's one of the things that inflation does. As soon as you introduce a cosmological constant, you lose that nice property. The spatial curvature might be now spatially flat, but I've introduced another problem of why is the dark energy only becoming dynamically important now? So it makes the theory ugly again. And that problem is not solved to this day. We have no understanding of why dark energy is becoming dominant only now, okay? So, but it was this ugliness. Have a pretty theory, and now, because of some guys with photographic plates, they're telling us that we have to drop this, it was not well received, okay? So these were the years, after 1990 for me, scientifically, were kind of sort of dark years of, not being, having this beautiful work that we've done not being well received. But it was lightened up at other times, and here's Catherine. Is Catherine in the audience? Oh, there you are. So here's Catherine, and beautiful, beautiful cake here. And this was a big surprise, okay, because the department made this cake with the APM survey. They actually, put the APM survey in icing, on the cake for my 40th birthday. So that was the upside. We've got, people might not have accepted lambda, but we got a nice cake. So, and here's me and Catherine, and here's Phil Charles. For those of you who know Phil Charles. So youthful-looking Phil Charles, who was always first to the booze, as you can see. And since now I'm going through the family snaps, here's another one. And here's a youthful Roger. Roger hasn't changed that much. It's really quite remarkable. And Yo. Okay, so, and this is my daughter, Zoe. And I don't know, Roger, do you remember what this picture was, what the event was?
I think, is it Lucy James's mother?
Exactly, yes. It's from the, it's a photo from the Binney wedding.
Yes.
Yeah. So where do we go from there? Okay, so then two major events in quick succession. First was in 1992, the discovery of the fluctuations in the cosmic microwave background by the COBE satellite. Highly, highly significant discovery. And incidentally, as soon as we knew the amplitude of these fluctuations, it fitted with the lambda CDM version of the model. Okay, so a model without a cosmological constant would have predicted a lower amplitude of the fluctuations than Kobe observed. So that was a very significant discovery. It started a big observational activity now that the fluctuations had been discovered. People knew what the amplitude should be to improve the sensitivity and angular resolution of the measurements. And that led to the Planck satellite. And then in 1998, there was the announcement of the discovery of an accelerating universe from observations of type 1a supernovae. And so this is one of the discovery plots showing the constraints. So this is using type 1a supernovae as standard candles to determine the expansion history of the universe. And it shows the density in units of the critical density in a lambda term versus the matter term. By this stage, the CMB there was already evidence that the universe was spatially flat. So you had to lie on this line, and you can see that required that most of the matter content in the universe was dominated by a cosmological constant. So things were very well set up, and this result was basically accepted by the community overnight. So big change. So then, following this massive activity to measure the power spectrum of the cosmic microwave background anisotropies. And I've got a sequence of plots showing how those measurements improved. Remember, Kobe announced their discovery in 1992. Here, by 1999, there were a bunch of experiments, ground-based experiments, not altogether consistent with each other, as you can see from the green points here, but showing hints of a first acoustic peak. Okay? Then, in 2003, before WMAP, the NASA satellite returned its results, very, very clear evidence of a first acoustic peak at just the right location that you'd expect for a spatially flat geometry in the universe. So, the boomerang experiment was very, very influential in establishing that the universe was very close to being spatially flat. Then WMAP flew, and so this is a state of play by 2009, which was the year in which the Planck satellite was launched. So you can see now you've got maybe 2.5 acoustic peaks mapped in this spectrum. And then we published the first results from Planck in 2013. And here are the results. Now, just a giant leap in precision. Okay, so the red line is an inflationary adiabatic lambda CDM cosmology. And the blue points are measurements of the power spectrum from Planck. The scale is divided into a logarithmic scale at low multiples, so you can see what's going on here, and then linear at high multiples. So these are band average, and when you average the power spectrum in multiple bands of, in this case, delta L of 31, you can't see the error bars anymore. So I've plotted the residuals in the lower panel. The little grey points are the individual power spectrum amplitudes as a function, multiple by multiple, okay, before averaging. And you can see that the fit is absolutely brilliant. Okay, so, I think, when you get something like that that agrees so well, it's quite reasonable to say that there's a degree of truth in the theoretical explanation. So we have a fit to an inflationary motivated lambda CDM cosmology that fits extremely well. There are various little bumps and wiggles, but in 2013 we published just half the data that we had, what was called the nominal emission from Planck. And so in, by the time of the final Planck papers, we analyzed all of the data, and you can see that all that happened was that the fit to the ΛCDM cosmology just improved in accuracy. And there were still a few bumps and wiggles and so on, and so after we did the final set of Planck papers, I worked for basically for an entire year trying to extract yet more information out of Planck, and the only real way that you can do that is to increase the sky coverage. And to increase the sky coverage when you have foregrounds, you really do have to know what you're doing, and it would take a long, long talk to explain how that's done. But I'll show you what happens. So here is the 2018, just now eliminating the low multiples so you can zoom into the high multiples. Here is the power spectrum, and then you push the data, and you can see just by eye that it's quieter and an even better fit. The parameters don't change. You just get a tighter fit when you push the data. So that's just showing the same thing on an expanding scale. So I spent a year pushing the data, and all I succeeded in doing, this was done with Stephen Grattan, all that we succeeded in doing was getting an even better fit to the ΛCDM cosmology. No funny features, any indications of any new physics or whatever. It's just ΛCDM, okay? And we also, got very good measurements with of polarization. And so this shows power spectra showing the temperature to E-mode cross power spectrum. So a temperature polarization cross power spectrum. The blue dots are Planck. And then what I've shown you is the recent results from the Atacama Cosmology Telescope that Joe Dunkley is very heavily involved in. And the ACT data, you can't really see the error bars very well. They're not as precise, nothing like as precise as Planck on these scales, but they extend to very small angular scales, which Planck just can't sample. And this red line is just what we'd expect from the Planck cosmology. So it's not fitted to the ACT data, they've done the experiment, and you can see that it fits very, very well. And then there's another large ground-based dish at the South Pole, and they announced their results, not going to quite as high resolution as ACT, but for the same power spectrum, beautiful agreement, and then you go to higher multiples, sampling small scales, then that's also a very good fit. And then for the polarization power spectrum, this is pure polarization now, just E-mode power spectrum. Planck is not so good at this because its sensitivity limits it, so we can't really go to high multiples. But the ground-based experiments, they do go to high multiples, and here is exactly the same thing now in polarization, showing that the Planck cosmology fits the ACT data and the South Pole Telescope data to very high angular resolution. So the model fits exquisitely well, and it fits other things very well as well. So here is the map of the temperature and isotropies, and the significance of this is that all of this information that we've collected on temperature, polarization, gravitational lensing of the cosmic microwave background, etc., you can compress all of that information into just 6 numbers. And that's the significance, that's the real significance of the ΛCDM cosmology, that you can get this massive data compression down to just 6 numbers. So you'll have noticed that so far in this talk, I've not shown you constraints on any of the parameters. And it's because, to me, that doesn't matter. If you want to see error ellipses of parameters, here's an example showing constraints on the Hubble constant. This is the physical density of baryons, omega b times h squared, the physical density of cold dark matter. This is the location parameter that gives you the location of the acoustic peaks. So this tells you what the curvature of the universe is, the scalar spectral index, and then the amplitude of the fluctuations. And this parameter here is a parameter that weak gravitational lensing surveys measure. And you can see the constraints, and you can also see on this plot the consistency of the constraints from temperature and the temperature E-mode polarization spectrum. That spectrum alone is nearly as powerful as the temperature fluctuations. So in the ΛCDM cosmology, these are the kind of constraints that you get. And do you know the Martin-Rees scale of odds? Okay, so Martin, he always asks, is some result right? Okay, so is some result right? Then the question is, would you bet your goldfish, your dog, or your life? Okay, so those are the choices, and so if you ask, are the Planck parameters reliable, then I would bet my life. Okay, I know the data intimately, and there's no way that those numbers are wrong. Okay, so if you find something that deviates away from this, then you've got evidence for new physics beyond the ΛCDM cosmology. As I said, there's 6 numbers. So here are the relevant fundamental numbers, the physical densities in baryon, it's cold dark matter, the location parameter, the optical depth to reionization, which is not a fundamental parameter, but you need to constrain it. The scalar spectral index, so n equals 1 would be exactly scalar invariant fluctuations. So the fact that it isn't 1 tells you about inflation. And then the amplitude of the fluctuations. And then these other parameters are derived parameters. You can derive those parameters. But as I said, it's not the values themselves that are really the things that I want to focus on. It's the fact that that you can explain an awful lot with just 6 numbers. Okay. So do we have a standard model of cosmology? Well, yes. We clearly have a standard model of cosmology, the ΛCDM model with those 6 numbers. But inflation is not understood, dark matter is not understood, and dark energy is not understood. So we have a standard model of cosmology, but it's not a model that you should be happy to boast about, not to your particle physics colleagues or to your condensed matter physics colleagues. We don't know what 95% of the universe is, but we've measured these things that we don't know very, very accurately. That's not a great selling point, okay? So we do have a standard model of cosmology, but it's really not a very good, satisfying model. If I go back to when I was very young, we've seen this tremendous change in cosmology, but am I any the wiser for knowing that ΛCDM fits the data when I don't understand all this stuff? Okay, so I think that's a real problem. Is ΛCDM just a fitting function? Is it just a mirage? Okay. Subia might say so, but so is it epicycles? I don't think so. I think that the fact that it fits so much data, it tells you that there's truth in it somewhere. But we don't understand the model. And then there are features that really aren't quite what we were expecting. And so let me just recap what has happened. The model, we've built this model through a series of paradigm shifts. So the first was the discovery of the cosmic microwave background itself when I was age 10. The inflation, and particularly the quantum origin of fluctuations in the universe, in 1982, when I was age 27. The discovery of cosmic microwave background anisotropies when I was age 37. The discovery of dark energy when I was age 43. And there's been nothing in the last 23 years. Okay? So, in terms of development of cosmological theory is concerned, there's been silence for 23 years. So going back to when I introduced this talk of, does the subject begin when you start your PhD? If you started your PhD in 1998, when all of this is history, you would be 44 now. You'd be a mid-career scientist. And you've not experienced any of the paradigm shifts. I had loads of them when by the time I was 44. Okay, so where is the subject going to go, given this? The universe has told us that it's locked onto this ΛCDM model, but there's been no indication of anything else, convincing indication of anything else since. So I want to spend the last, I'm going to have to compress it, last few minutes just looking at, is the theory likely to shift? And if so, where? Where is it likely to shift? So the first thing is on inflation. Inflation, whatever anybody says, inflation is not what we'd have expected. The constraints, the inflationary models that are consistent with the Planck data and with observations of setting limits on gravitational waves, they're not what we'd have said was natural before we started making these measurements. This is shown on this diagram, which is indicating the tensor to scalar ratio, the amplitude of the fluctuations on large scales that come from gravitational waves relative to scalar fluctuations as a function of the spectral index. And the key thing is to look at this ellipse here, because these are the latest results from the BICEP-Keck collaboration searching for B-mode patterns in the polarization signals on large scales. So their experiment sets the limit on the tensor to scalar ratio. Planck sets the limit on the scalar spectral index. And this shows you the expectations for different potentials in inflation. We don't know exactly how many e-foldings of inflation there's been, but we would expect for a phi squared potential to sit somewhere here, for a potential that depends linearly on phi to sit somewhere here, and so on. What we've learned from these constraints is that the inflationary potential is unusually flat. There's a fine-tuning in when you construct an inflationary model, there's a fine-tuning in the slow roll parameters of inflation that's not understood and not expected. So that's an unusual result, and it's pointing us to something important. Another thing is the constraints on the equation of state of dark energy. So here's the simple parameterization that a lot of people use. W naught equals -1 is a cosmological constant, and WA parameterizes some time dependence. And so here are constraints in WWA space from Planck combined with baryon acoustic oscillation data and supernova data. The thing is that these regions of the diagram, the equation of state is less than -1 at either always or at some point in the universe's history. And so it's a phantom-like equation of state, which is very difficult to realize theoretically. So the constraints for conventional equations of state, you have to sit somewhere here. And the data it's so close to a cosmological constant that, again, if you're trying to make dynamical models of dark energy with scalar fields and so on, you need an unusually flat potential. So the data is, and again, that involves fine-tuning of parameters. You can see this because there's a nice little equation which you can derive that gives you the first derivative of quintessence potential in terms of the equation of state parameter. And the closer you limit the equation of state parameter to -1, the cosmological constant, the smaller in Planck units this derivative. And it's already, unnaturally small. So inflation and dark energy are both pointing, if dark energy is dynamical, towards very flat potentials, which is weird, because there are string theorists who have been arguing the exact opposite. That, so the idea here is that there's a theory of, a quantum theory of gravity, a so-called UV complete theory, that may be string theory or something like string theory, and the sort of low energy quantum field theory is that we make it constrained by the quantum theory of gravity. So not everything that you can write down, you just write down a Lagrangian, that does not necessarily mean that it's a viable theory consistent with a UV complete theory of gravity. And so there's been speculation of what these constraints might look like. And here are the speculations by a number of string theorists, which is the exact opposite of what the data want. They want steep potentials for inflation, steep potentials for dark energy, okay, and the data saying the opposite. So there's potential for theoretical development there. Also, inflation is eternal, and this raises a whole issue of calculability if you have a multiverse consisting of number of infinite universes. Okay, so that is, I think, a serious problem for inflation. So, are you likely to get observational paradigm shifts? Well, there are some problems. The value of the Hubble constant, determined from the cosmic microwave background, the best fitting value from in the ΛCDM model, disagrees with some measurements of the Hubble constant, direct measurements using variance of the distance ladder. So I'll give a technical talk about that tomorrow. And then weak lensing surveys. Remember, this parameter is constrained by weak lensing surveys. Here they are. These are results from the very recent results from the KIDS survey. And here are various other ways of getting this amplitude from the cosmic microwave background, from other data combinations. And there are hints of a discrepancy there. So, where is the next paradigm shift likely to come from? Well, it could come from theory, and we could get some sort of compelling reason for these fine-tunings for why the inflationary potential has to look the way it is. So that's a possibility, but don't bank on it. I mean, I said there have been no paradigm shifts in 23 years. The last good theoretical idea in cosmology was inflation, which is 40 years ago. So the theories have not really done very well. So it's possible, but I wouldn't bank on it. These tensions between the Hubble constant, weak lensing, those have to be investigated very thoroughly because there is something going on there, either with the theory or with the data. CMB large-scale structure, we could determine neutrino masses, and that's feasible to do, but potentially not very fundamental. I mean, in the sense of introducing a paradigm shift in the way that we think about cosmology. Gravitational waves, that would be a paradigm shifting measurement, if we detected gravitational waves from the early universe, but it may be impossible. Deviations from Gaussianity, that's also subject of a lot of interest, but may be impossible. And there's direct detection of dark matter, and that's my bet for the next paradigm shift. That, I would think that it's, that would definitely be paradigm shifting, and is the most plausible, I think, of these, of these potential sources of new thinking. So, where is the subject going to go? in the next few years? Well, you know, the next generation of scientists, you are really well funded. Okay, so you know, you can't say that you haven't been given a great chance of making new discoveries. You've got all of these facilities coming online, run out of time, so I'm not going to talk about them. And so it's up to the next generation. Use these facilities, use them wisely, and hopefully, if you're lucky, there'll be some paradigm-shifting discoveries as a consequence. So all, you know, I mean, all I can say is if you fail to make any discoveries with all of those billions of dollars worth of equipment, then you better read Offer's article of when to stop, okay? And so with that, I just wish you the best of luck, and you know, may the force be with you. So thank you.
Thank you very much, George. I think before you started speaking, we all knew that Dick Dalitz was a great man, but now we know he had great judgment. Thank you. So let's take a couple of questions from the room, and then we'll take some questions from those online. So who's first? Gavin? Can we get a mic to Gavin and then to Tim? So actually, let's take Tim first, because Amy, you're next door to him there. Look, that's it. And then get a mic to Gavin for the next one. Tim.
Speaking as a non-cosmologist, as I understand it, the universe, or the standard models of the universe predict or assume that on the larger scales, the universe is homogeneous and isotropic. I just wondered on Martin Rees's scale, how strong your belief in that is.
Oh, so yes, okay. Well, so it depends on what scale. I mean, look, we've measured the temperature and isotropies on, you know, from the microwave background, and we have sensitivity. You know, when you measure the quadrupole, it's being influenced by fluctuations that are larger than the Hubble radius, present Hubble radius. So in the sense of, you know, is our universe, is there evidence for, you know, for isotropy, then the experimental evidence is very good, but we can't tell what's happening on scales much larger than our present Hubble radius. And inflationary cosmologies, then the universe, you know, could be very inhomogeneous on very large scales. But yeah, I would have
Was that a goldfish answer?
It's dog answer. It's dog. Dog. I wouldn't go. You know, I would certainly bet my least favourite member of my department's life. How about that? As an intermediate.
Gavin and then Rosemary.
Is this working? Yes. Okay. So I'd just like to bring you to your last point and ask you to go a little bit further. So direct detection of dark matter as a way forward. Do you see any future in looking at the dark matter structure of the Milky Way, or do you think it comes from the labs and ground-based particle physics?
So no, I'm agnostic about that, and so my thinking there is that simply that, you know, dark matter is a fundamental ingredient of the model, and we don't know what it is. The idea that it's just cold dark matter with you know, there may be multiple components of dark matter. There's no reason to accept, you know, to believe that the dark sector is extremely simple. We already know that it isn't, because neutrinos contribute about the same as the baryon density, and they belong to the dark sector. Okay, so so there may be you know, components with different cross sections, different interactions. We just don't know. So you know, but search for it.
Okay, before we get a mic to Rosemary, let's see if there are any questions from those watching on the web. Do you have anything?
Yeah.
Go ahead.
So just to follow up on the the dark matter.
Oh, we need a mic here. Sorry, I beg your pardon. Yeah. Thanks, Anastasia.
Just to follow up on the dark matter, what it is in your opinion?
I'm far too modest to express a view on what it's whatever the universe has decided it is. Okay, so supersymmetric relic, okay, is a good bet. But opinions. Different people have different opinions. So I'm agnostic.
Peter, do you have one or another one? Anastasia, do you have?
Why do you think the progress has slowed down in cosmology when in most other fields increased computing power has greatly increased the speed and advancement? And follow up on this, do you think LISA has an opportunity to discover CMB gravitational waves?
Right. So on the last point, I think it's very, very unlikely that you would, that LISA will detect, some sort of, preheating type signature or some other signature of gravitational waves. So, the problem has not been, lack of computer power or lack of investment in observations and so on. The lack of paradigm shifts has been because the lambda CDM model fits so well. And the more data that we get, the more accurately it fits, apart from a few anomalies. So it's the universe's fault. Okay? And if you ask, okay, so next generation scientist comes to give Hintze Lecture, in 50 years' time, and says it's lambda CDM all the way down. Okay, that's a real possibility. Okay, but may the force be with you. This final thing is really saying that I hope you're lucky, and that you discover things. So maybe the universe has surprises for us. But it could be lambda CDM all the way down.
Rosemary, and then... Oh, your question was answered. Okay, so at the back here, can we get a mic up there to the back?
Hiya, I'm a neutrino physicist as opposed to a cosmologist.
Can you take the mask down?
Oh, yeah, sure. Yeah, I'm more of a neutrino physicist than a cosmologist. So your comment at the end about measuring the absolute mass of the mass scale of the neutrinos is quite interesting. I know that is it the Planck measurements that currently have the best limit? I think.
So the current constraints on neutrino masses from cosmology are actually really quite good. I mean, I've got a diagram here. It kind of. No, it doesn't. Do I have a neutrino mass constraint? I don't have a neutrino mass constraint to show you. But the 95% upper limit is about 0.15 EV. So it's not far off 0.06. Okay?
Yeah, so do we think that in the near future we're actually going to be able to measure it cosmologically?
It's a feasible thing. It's not easy, but it's a feasible thing for next stage CMB experiments and large-scale structure surveys to actually detect a neutrino mass and to tell you whether it's a normal hierarchy or an inverted hierarchy. My comment at the end was that, let's suppose that that cosmology, tells you that it's 0.06 EV. That's not really a surprise, is it? So it's not paradigm shifting. I mean, so when I gave a version of this talk at UCL, people said, well, look, you said nothing's happened in the last 23 years, but gravitational waves have been discovered. Fantastic discovery. But so far it hasn't changed our thinking about gravity. It's consistent with general relativity. And to qualify as a paradigm shifting discovery, you'd have to detect gravitational waves and show that there's a deviation in the strong gravity regime from the predictions of general relativity. Then it's real game changing. So my criteria for paradigm shifts, I've set it very high.
You need something like a neutrino oscillation, something equivalent in what we weren't looking for. What's the comment about?
So something that changes the way that we think about theory. So on that kind of thinking, even if you detected CP violation in the neutrino sector, it wouldn't qualify as a paradigm-shifting discovery. You've determined a parameter that we have no reason to expect is not non-zero. So.
Okay, let's take one more from online and one more from the back there, David. Okay, bring it down here. Yeah, and then we'll wrap up.
Lots of people really enjoyed the talk online and got lots of questions. So here's a kind of personal one from some of the things. What's the biggest thing you've changed your mind about in terms of the universe and cosmology over your career?
The biggest thing that I've changed my mind about? Wow. Oh, what a question. Dear oh dear. You have actually stumped me. I think that the biggest thing that I've changed my mind about in, say, the last 10 years, since the Planck results, are my views about inflation. Because inflation, there are people like Paul Steinhardt, very clever people like Paul Steinhardt, Neil Turok, Roger Penrose, that really, have argued against inflation. That it's not as good a theory as the majority of the community think it is. And these are not stupid people. I think they have a point. And I think that I've changed my mind in the sense of, instead of saying inflation is a fantastic theory, it's a great theory, to thinking the parameters, there are problems with inflation. There are problems with initial conditions. So inflation is an incomplete theory. That doesn't mean that inflation is wrong. I wouldn't go as far as, Paul Steinhardt and Neil Turok and say that, inflation is a bad theory, whatever. But it's an incomplete theory. And so we mustn't be complacent. So I think my view of inflation, I've become more concerned about the incompleteness of the theory, over the last few years.
Okay, thank you very much, and thank you to everybody online who asked questions. The last question is from Matt.
So I guess a slightly broader question looking forward. So all the big paradigm shifts that you mentioned from the observations have come from teams or people that are very much connected with the data and working with the data and analysing the data and doing the science at the end of the data. But with the new facilities, we have teams working with the data, and they're not necessarily the people producing the science papers at the end, although there's lots of involvement. So there started to be a disconnect of those people that know the data and those people doing the hard analysis at the end of the process. So how do we get over that in these big teams?
I actually do think that's a point of concern. Planck was at the scale that no individual could understand everything from, the time-ordered data, right the way through to the science. But we were very close. And some of the big stuff has become so compartmentalized that no individual has an overview of the whole project. And so I think that's problematic. So I think that you could well see a series of great claims of results that will turn out to be wrong, because of that.
Well, that's a rather sobering note to end on. However, I'm going to call it a close because we've had a terrific lecture and a lot of questions. So thank you, everybody, for online. Thank you, everybody, for coming. And most of all, thank you for George for a tremendous lecture. Thank you very much.